Hello there guys, this is Teacher Krishna and welcome to our next class for the third unit. This is a class that is part of a high school and a high school. Our subject is science and of course our week is number 23. I'm pretty sure that you can notice that there is not a video of myself right here. Well, the problem is that today's lesson is going to be a little bit longer than 15 minutes. And the other program only allows me to record myself for 15 minutes. So we're still going to have a class, but it's going to be like just like in the way we had it during the second unit. Alright, so let's go over our presentation. And remember to have your notebook with you in order to make today's summary. The parts of the summary are the following: date, ending mind, title, of course the summary itself, and remember to add some additional decoration to your summary. Alright, let's continue. Today we're going to be learning about topic 4.03b, stars and elements. The ending mind for today's topic is the following. Students will be able to determine the way the first elements of the universe were created, and the way their several changes when affected by several forces lead to the creation of stars. It is a very interesting topic that we are going to be learning about, and of course we're going to be taking a look at the creation of the universe from a scientific point of view. Alright, so what activities do you need to do today? So the first one, of course, is watching this video and making a summary of it. Then you need to read topic 4.03b and complement your summary. Just like every week, I include most of the information from the topic, but I always like my students to reinforce their reading skills by reading a couple of pages. So today specifically, please focus on pages 5 and 6. Then you need to complete the worksheet. Go to page number 6 of topic 4.03b. Download the Stars and Elements worksheet and of course complete it. Just in case you are having any problems when completing the worksheet, you can always contact me in WhatsApp so I can help you out by giving you some additional support. Okay? And besides that, remember, when you finish with your worksheet, you have to upload it to Academics to the same evaluation of topic 4.03b. Right, make sure to download that document and work on it afterwards. I'm not going to share it with you because right now it's a little bit more difficult to actually share documents in Educativa, but you can download it right over there. If you have any problems by downloading it, you can let me know. Alright, so let's go over our topic, stars and elements. And this is a very beautiful picture. I don't think it's real, but it is still very nice looking. So we start by saying that 15 billion years ago the Big Bang took place. It was a gigantic explosion that released an unmeasurable amount of energy. So a while ago, scientists were trying to theorize how the universe was created. Because before science, religion will say that God was the one that created all the universe and all of the things that we can see around us. But scientists try to look for a different perspective or a different theory, and based on that, they created the theory of the Big Bang. In which, of course, due to a gigantic explosion, a lot of energy and matter was distributed around the universe. And it says before the stars were formed, high energy collisions took place from proton and hydrogen atoms. After billions of years, neutrons led to the creation of other elements, such as helium. Keep in mind that elements in a star fluctuate along the stages of their life. So, something very interesting that we are going to learn about today is that the first composition of any star is going to be hydrogen. But after a while and after a lot of nuclear fission or nuclear fusion, what's going to happen is that the hydrogen is going to be turned into other elements such as helium, lithium, we can continue with oxygen and a lot more. Alright? But this is just a small introduction how the elements inside a star are going to change. After a while, galaxies were formed as well. So, the first thing that happened, according to scientists, was the Big Bang. Then a lot of stars were formed, and then we had resulting galaxies, planets, meteorites, and much more. Alright, so we have the nuclear engine of a star. So this is a very interesting picture to analyze because it's related to what I was telling you about. So just like you can see right over here, the blue circles are going to represent products. The yellow circles are going to represent the neutrons. Then the white parts are going to represent the positron. Then we have the neutrino, and we have the gamma rays. Alright, so basically what happens is that protons are interacting with neutrons inside a star. And when protons and neutrons start interacting within each other, they are going to create new elements. Like if we talk about hydrogen, for example, so in hydrogen, we are going to find very little protons and neutrons. But once they get more, they can turn into helium, into lithium, and so on and so forth. Alright, so hydrogen and helium are the star's fuel. Of course, and remember that because of the nuclear fusion that we find in stars, they create a lot of energy, but gigantic amounts of energy. And the engine of our sun is a process called nuclear fusion. Nuclear energy produces way more energy than chemical energy. So, an example of nuclear energy is, of course, the recombination of protons and neutrons, just like we can see right here. And an example of chemical energy can be like when you burn down a paper. So, when the paper is on fire, of course, it is producing energy. But the difference between nuclear energy and chemical energy is gigantic. We have nuclear power releases large amounts of energy and radiation. Nuclei combines to form heavier elements, which means that hydrogen changes into helium. This is the most enigmatic example that I have given so far, but of course the elements can change way more. And from hydrogen to helium, from helium to lithium, and it continues until it reaches iron. Why does it continue until it reaches iron? Because what happens is that even though there is still nuclear fusion, when iron is changed into other elements, the amount of energy that is being released is not as much as the one that is being released with other elements that come before iron. And this process is called nucleosynthesis, which is pretty interesting. Alright, and here we have a table of elements, and right over here you can actually notice all of the pattern that the elements are going to be following. So of course we start with element number 1, which is hydrogen. Then we are going to continue with element number 2, which is right here, which will be helium. Then from 2 to number 3, and from 3 to 4, 4 to 5, so on and so forth. We continue until we reach iron. Alright? And right over here what's interesting is that scientists are going to use the elements of a star to determine the stages in their life. So, for example, we have the Big Bang fusion, which is like the earliest the creation of a star. It's a star that is just being born. So it'll be the color sky blue or blue, which will be, of course, hydrogen and a little bit of helium. Of course, in lithium as well. But how about a dying low mass star? Remember, this one will be one of the last stages of the life of a star. So in green, we are going to find, for example, carbon, we're going to find nitrogen as well, and much more elements that are colored in green, of course. And so on and so forth. We continue with exploding massive stars, human synthesis or no stable isotopes, a cosmic ray fission, emerging neutron stars, and of course exploding white dwarfs. And exploding white dwarfs is one of the last stages in life of a star as well. Alright, so let's continue. And let's continue talking about the star's life. And this will be just a small summary because we have already studied the life cycle of a star. But anyways, let's continue. The star's life is mainly determined by its initial mass. Our sun is considered a low mass star or an intermediate mass star that lives for around 10 billion years. To determine the age of a star, scientists analyze the percentage of light and heavy elements. Remember, light elements are the ones that are in the first stage of the life of a star. And the heavy elements are the ones that are found like in the middle or at the end of the life cycle of a star. And this one is the life cycle of a star that has a low, which means that it has very little materials that actually conform it. So stars are born from clouds of hydrogen, helium, and dust. If helium is enough, nuclear fission starts, and massive amounts of energy are released. Of course, this is the very first stage in the life of a star that has a very low mass. Then the star enters a phase of instability in which they grow enormously. They form a red giant. After a while, the star loses some of its layers. They form a planetary nebula. All right. So this is interesting, but in the second stage of the life of one of these stars, they are going to grow a lot. So probably they were little at first, but then they are going to be big. And with time, the remaining parts of the star forms a white dwarf and will end its life as a black dwarf. So after it has grown a lot, it is going to start losing a lot of material from the outer layers of the star. And of course the remaining materials are going to be a white dwarf, which is a star that is not bright. It has a very dark tone, let's say. And it will continue consuming the materials that it has until it stops being bright. And of course it will turn into a black dwarf. Alright, and now we're going to talk about high mass stars life cycle. And stars are born from clouds of hydrogen, helium, and dust, which is pretty much the same as the previous stars. Slowly, the hydrogen is converted into helium. It consumes its hydrogen very quickly, so it can maintain its stability for around 5 billion years. This is something very important to analyze because remember that in the stars with a low mass, they do have hydrogen and helium. But since they are way smaller, they consume their hydrogen and helium way is slower. But in this case, since the stars are very big, then they need to consume the hydrogen and helium super quickly. So this stage of their life is going to last only 5 billion years. It's interesting to make that analogy, right? Like only 5 billion years. Of course, comparing the life cycle of both of the stars that we're just studying right now. Then it grows and becomes a supergiant. Remember, a star with a low mass is going to grow into a giant, a red giant, and that's it. But in this case, these massive stars are going to grow even more, and they are going to become like extremely big, and bigger, of course, than the other stars. That's why they are called supergiant. The nuclear processes continue until iron is formed. This is something very important. It continues until we reach iron. Right after, the outer layers of the star are attracted to the nucleus of the star, which generates an enormous explosion. The supergiant becomes a supernova. So, what are some of the differences between a supergiant and a supernova? Well, a supernova is going to be smaller than the supergiant, but all of the materials that it is going to contain are going to be way more compact inside the star. Then the supergiant compacts until it forms a neutron star. So basically, a neutron star is extremely small compared to other stars, but it has a gigantic amount of gravity and, of course, an enormous amount of elements that are way too compacted inside. Alright, and here we have a picture of what it will look like. Of course, taking into account all of the stages of the life cycle of a star. So, of course, we have a molecular cloud, and after the molecular cloud is formed, then a lot of materials are going to be compacted inside one object, which is going to be a star. And right over here, you can have three differences. You can have a massive star, a low mass star, and a brown dwarf. So a brown dwarf just stays like that. It has no more stages later on. Alright? But if we continue with the low mass star, remember, it is going to continue consuming the hydrogen and helium until it reaches iron. Then it is going to expand until it becomes a red giant. Then from both, it can happen that the red giant turns into a planetary nebula, continuing with a white dwarf and, of course, the black dwarf. Or what can happen as well is that it can change into a binary white dwarf, just like you can see right over here. Then this binary white dwarf can turn into a type of supernova, which is not as powerful as the supernova that we see from above, but it's somewhat like that. It can become a nova as well. And then, of course, it will end up becoming a white dwarf and a black dwarf at the end. But what happens with the life cycle of a massive star? Notice right over here we have all of the nuclear fusion until it grows a lot, until the red supergiant. Then the red supergiant changes into a supernova. The supernova can change into a supernova remnant, or it can change into a black hole. This is something very interesting to analyze, because a star, when it dies, can become a black hole. And black holes are going to be emitting X-rays. And according to Albert Einstein and according to other scientists, the gravitational pull that we can find around a black hole is so powerful that it can even change time. Imagine, like, that's incredible. It's something that we haven't been able to look at with our own eyes and, of course, experiment around. But according to the scientific principles, it's mentioned that the gravitational pull that it has can cause changes in time. It's amazing. And also a supernova can change into a neutron star, and of course a neutron star will be generating pulsars. Alright, so the first part that we see right over here is the birth of the star. Then we have the main sequence, which is right here. We have the old age, we have the death of the stars, and lastly we have the remnant. Alright, now we have the star aging, and this is something very interesting as well. So as the stars grow old, they change their color. Alright? And low mass stars, they produce nuclear fusion in all parts of its body. Intermediate mass stars, they have a radioactive core and are surrounded by a convective region of nuclear fusion. And large mass stars energy production is concentrated in the center. Alright, so the picture that we see right over here is a low mass star. Just like you can notice, it is producing nuclear fusion all around. Alright, in intermediate mass stars, the energy is usually produced in the outer layers. And we have several chemical reactions from the middle that are taken out to the outside layers. And right over here is where energy is produced. Then with the large mass stars, the energy is focused in the center of the star. Of course, several energy is being rejected from the center, but most of the energy is concentrated right in the middle of the star. Alright, and right over here we have some information related to supernovas. And we have a type number 1 and type number 2. Remember that the supernova from type number 1 is a kind of supernova that is formed when we follow the life cycle of a star that has a low or an intermediate mass. And the supernova from type 2 is the supernova that is formed when we follow the life cycle of a star that has a very high mass. So let's analyze each one of these aspects we have. The lack of hydrogen and helium at its core. Well, both of them lack both materials. It retains most of the remaining lighter elements in outer layers of a star. Well, this is going to happen only with the type of supernova number 2, because remember that most of the energy is centralized in the middle of the star. At the threshold mass, the star implodes. Both of them happen in the same way. Massive enough to fuse to carbon iron without borrowed energy from nearby stars. Well, this only happens with supernovas right over here. Because in the first one, it doesn't have enough energy in order to change, let's say. So it needs some additional energy to be able to change. And where is it going to get that energy from? Well, it will have to be necessarily from stars that are close by that have generated an explosion. And that explosion that has transmitted energy has to be high enough in order to support the supernova to change. And explodes remaining layers of hydrogen and helium into space. It will apply to both of them. And we have some general information. Some telescopes detect visible light. Others detect electromagnetic spectrum, and some others can detect gamma rays. Rays produced by the gamma rays are the ones that are produced by the hottest objects in space. Electromagnetic emission is used to determine the composition and age of a star. It also helps to determine how far away it is from Earth. They have some types of electromagnetic waves from smaller to larger. So the smaller waves that we have are radio waves, and they actually reach Earth's surface. They are picked by radio telescopes, and they can reveal the existence of pulsars. Remember, pulsars are one of the last, or most likely the last step in the life cycle of the stars with a high mass. We have microwaves. They are used to precisely measure temperature variations in the universe. We have infrared waves. They are longer than visible light. And infrared waves, when they enter the atmosphere on Earth, are transformed into heat energy. We have ultraviolet waves. They are shorter than visible light and are used to study hot stars. We have X-rays. They are used to detect the presence of interstellar clouds. And lastly, we have gamma rays. They show areas where large amounts of energy are released. Oh, and we already reached the end of our presentation for today. So thank you a lot, guys, for coming to today's lesson. And I'm going to see you during the live session that we have in a couple of minutes. So I hope that you are doing well, and always take care, guys. Goodbye.